So, in the last session we had seen 3 examples. All the 3 examples were either linear programming or mixed integer linear programming. Today we will look into 3 additional examples which are based on constraint programming. We have not seen constraint programming as part of this course, but still we wanted to show you the feature of IBM ILOG CPLEX optimization studio to solve constraint programming problems. So, as part of this session we will be looking into 3 problems. The first one is map coloring problem. We will follow it up with a Pseudocode problem and a scheduling problem. So, in this map coloring problem, given a map, right, the objective is to color the countries so that no 2 adjacent countries are of the same color, right. So, in this case we have 6 countries: Belgium, Denmark, France, Germany, Luxembourg and Netherlands. So, the neighbors of Belgium are France, Germany, Luxembourg and Netherlands. The neighbor of Denmark is Germany. The neighbor of France is Belgium, Germany, Luxembourg. Similarly, you can look at the neighbors of the other 3 countries, right. So, all these countries are to be colored such that no 2 neighboring countries are of the same color. So, over here Netherlands and Belgium cannot have the same color, Netherlands and Germany cannot have the same color, right. So, if 2 countries are not neighbors, so for example France and Denmark are not neighboring countries, so they can have the same color, right. So, the colors which can be used is blue, white, yellow and green. So, this is the constraint programming model which we can code in IBM ILOG CPLEX optimization studio, right. So, when we want to use constraint programming, we need to explicitly specify that, right. So, we need to write using CP and a semicolon, right. So, if this line is not written, then it by default uses the CPLEX solver, right. Range we have seen previously, right. So, here we are defining range R which will have the values 0, 1, 2, 3. When we refer to R, we are referring to this 4 values 0, 1, 2, 3, right. So, here we are defining names, right, which is of data type string. It runs over R. So, we have names of 0, 1, 2 and 3. We provide the values, right. So, these are the 4 colors which we have: blue, white, yellow and green, right. So, strings are to be provided in double quotes, right. So, right now we have defined a range and we have defined as strings, and then we define these 6 decision variables, right. So, using dvar, right, and all these 6 decision variables are of the type integer, right. The name of the decision variables are Belgium, Denmark, France, Germany, Luxembourg and Netherlands. That is the name of the decision variable, and the range of all the 6 decision variable is in R, right. So, Belgium can take a value of 0, 1, 2, 3. Similarly, Denmark can take a value of 0 or 1 or 2 or 3. Over here we are just defining the decision variables, right, and for this problem we do not have an objective function, right. So, we do not write any objective function, we directly specify the constraints within these curly brackets. So, this constraint basically means that the value of Belgium should not be equal to the value of France, right. So, Belgium, as we know, can take any of these 4 values 0, 1, 2, 3, France can take again 0, 1, 2 or 3, right. So, this is, let us say, for France, this is for Belgium, right. So, the value of Belgium should not be equal to the value of France. So, here what we are basically trying to indicate is that if Belgium takes a value of 0, it means it is colored with blue. If it takes a value of 1, it is to be colored with white. If it takes a value of 2, it is to be colored with yellow, and if it takes a value of 3, it is to be colored with green, right. So, whatever color is to be assigned or whatever value Belgium is assigned should not be the same as the value of France, right. So, Belgium has this 4 countries which are neighbors, right. So, Luxembourg, Germany, Netherlands and France. So, that is why we write this constraint: Belgium not equal to France, Belgium not equal to Germany, Belgium not equal to Netherlands and Belgium not equal to Luxembourg, right. Similarly, the only neighbor for Denmark is Germany. So, we write over here Denmark is not equal to Germany. France basically has 3 neighbors, right, Germany, Luxembourg and Belgium. So, for Belgium we have written over here Belgium not equal to France. So, there is no point in again writing France not equal to Belgium. So, that is why we skip that thing, because that constraint is already been taken care. So, Germany has Denmark as neighbor, which is written over here. Germany has Belgium as neighbor, which is taken care over here. In addition, Germany also has neighbors of Luxembourg and Netherlands. So, this is how we write our constraints, right. So, these constraints are based on these neighbors, right. When we solve this, this is the solution. So, Belgium equal to 1, France is equal to 0, Germany is equal to 2, Netherlands equal to 0, Luxembourg equal to 3 and Denmark equal to 0, right. So, 0 indicates blue, right. So, it basically means that France is to be colored with blue, Netherlands is to be colored with blue, Denmark is to be colored with blue, Belgium is 1, right. So, it is white, Germany is 2, so yellow, and Luxembourg is green. So, this symbol exclamatory mark and equal to indicates not equal to, right. So, this equal to is for assignment, double equal to is to be used in constraints for conditional checking, and this exclamatory mark equal to is for not equal to. So, this map coloring example is already available. So, we can just import it. So, import from an example, right. So, over here in basic we have this color, right. So, if we double click on this, it opens a run configuration which is the basic run configuration, and it has a shortcut to the model color.mod, right. So, if we look at this color.mod, this is the piece of code which we discussed, right. We will not look into this, we leave it for you to explore it. So, till here this is the model which we have, right. So, to begin with, let us just comment this part, right. So, execution of this is similar to other files, run this configuration, right. So, we would get our values over here. So, Belgium is to be colored with 1, Denmark is to be colored with 2, right. So, 1 in this case is white, 2 in this case is yellow, right. France is to be colored with blue, Germany is to be colored with green, Luxembourg and Netherlands are to be colored with yellow. So, here it gives this warning message that we have not used this string, right. So, over here what we are doing is we are writing a script path with execute, right. So, write ln is used to write in a new line. So, what we want to write is the name of the country and colon, so that is given in double quotes. Then we have over here names of Belgium, right. So, once this model is executed, so now we have solved the model. So, Belgium is 1, right. So, when we write this basically says names of 1, and names of 1 is nothing but blue. So, when the problem is solved, Denmark will take a value of 2. So, names of 2 would basically indicate white. Similarly, we write for all the 6 countries that we have. So, we need to remember that this block is not part of the optimization model. It is just to display the solution in a user friendly way, right. So, if we execute this, so now if you see that warning message no longer appears over here, previously we had a warning message over here. If we look into this scripting log, we have this Belgium colon white, Denmark colon yellow, France colon blue, Germany colon green, Luxembourg colon yellow, Netherlands colon yellow, right. So, whatever is written within this double quote will be reproduced as such. Over here we are just extracting the appropriate color using the solution of the decision variable, right. So, the decision variables which is Belgium, Denmark, France, Germany, Luxembourg and Netherlands will take a value of either 0 or 1 or 2 or 3. So, this is how constraint programming can be used to solve the map coloring problem. So, now we will look into the Pseudocode problem. One of the classical applications of constraint programming is the Pseudocode problem, right. So, most of you would be familiar with Pseudocode problem. For those of you who do not know what is Pseudocode problem, an example of Pseudocode problem is shown over here, right. The standard Pseudocode problem consists of 9 rows and 9 columns. So, this is let us say R0, R1, R2, R3, R4, R5, R6, R7 and R8. It consists of 9 rows, right. We are starting from 0, that is why we are ending at 8, and it contains 9 columns. So, C0, C1, C2, C3, C4, C5, C6, C7 and C8. Right. We need to fill the 81 boxes with the numbers 1 to 9. Remember, 0 is not allowed. We need to fill with 1 to 9 such that no column has the same element repeated twice, right. So, for example, if we consider column 0, the numbers 1 to 9 should appear only once, right. If you consider column 1, the numbers 1 to 9 should appear once, and the same thing for the rest of the columns. Similarly, the rows should also have the elements 1 to 9 and the number should not be repeated. So, for example, in row 0, we have already filled the row 0 with 1, 7 and 9, right. So, the empty squares cannot take these values 1, 7 and 9. So, similarly for row 3 we have already used 1, 4, 6, right. So, the remaining this 6 elements cannot have 1, 4, 6. So, the rows and the columns should contain unique values. In addition to that, we have this 9 squares over here. So, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So, all these 9 squares contain 9 boxes, right. So, for example, if we consider this 7th box 1, 2, 3, 4, 5, 6, 7, 8, 9. So, similarly the rest of the boxes also contain 9. So, these 9 boxes should also have the values 1 to 9 occurring only once, right. So, for example, in this box 5 7 and 2 have been used. So, these rest of the empty boxes cannot have the value of 7 and 2. Similarly, this box 6 it already contains 3, 6, 7, 9. So, the remaining boxes in 6 cannot have the values 3, 6, 7 and 9, right. So, there are 3 types of constraints. The row should be unique, the column should be unique and the 9 3 cross 3 boxes should also contain values uniquely. So, now if you see this is a constraint satisfaction problem. So, previously we had seen what is constraint satisfaction problem. In constraint satisfaction problem we do not have a objective. So, there is nothing to minimize or maximize, but we have a set of constraints which have to be satisfied. So, a constraint satisfaction problem can always be converted into an optimization problem, right. So, for example, we can say that all the constraints are to be satisfied whatever we discussed. So, let us say this box is 8, 8, right. So, we can say minimize x of 8, 8 such that fill the rest of the entries, or even we can convert this problem as minimize 1 subject to the satisfaction of all the constraints, right. So, the objective function value would remain 1, it is just a constant, but we have constraints, right. So, every constraint satisfaction problem can be transformed into an optimization problem. So, now we need to see if we can transform the constraints, right. So, for example, here if we say this is x 0 0, x 0 1, so then we have a constraint which says x 0 0 should not be equal to x 0 1, should not be equal to x 0 2 and so on, right. So, such constraints have to be written for each of the other variables. Now, if you remember our previous discussion, for mathematical programming our constraints need to be of the form g of x is less than equal to 0, h of x equal to 0. So, this will accommodate both linear as well as non-linear constraints. So, now the question is to transform such constraints involving not equal to into this form, right. So, for Pseudocode problem it is possible to convert these not equal to into constraints of this type, right. So, but we will not be looking into that. What we will do is, instead of converting into a mixed integer linear programming or mixed integer non-linear programming, we will solve it with constraint programming with the help of IBM ILOG CPLEX optimization studio. So, this is the code for solving Pseudocode problem, right. So, the first line is using CP, because we want this code to be solved using constraint programming. If we do not give using CP, it will use CPLEX to solve it, and CPLEX will not support some of the constraints which we are writing in this model. So, we need to include this line using CP since we want to solve it with constraint programming, right. Then we are defining range, the name of the range is D and the values is 0 to 8. So, the values of range are 0, 1, 2, 3, 4, 5, 6, 7 and 8, and then we have a variable, right, whose name is input. This is not a decision variable, it is a parameter, right. The type of the parameter is integer, input d comma d, right. So, input d comma d means since d ranges from 0 to 8, input would be input of 0 comma 0, 0 comma 1, 0 comma 2, 0 comma 3 all the way up to 0 comma 8, right. And similarly it will be 1 comma 0, 2 comma 0. So, this will go on for 81 elements all the way up to input of 8 comma 8. So, in Pseudocode problem at times some of the values are already filled, right. So, for example, if we see this Pseudocode problem, these values were already filled 9, 6, 4, 1, 6, 1. So, those values can be input using this input d comma d, right. We have 3 dots over here, which means that the data is coming from an external source and it is not within the model, right. Then we define decision variable. So, the decision variable in our case is going to be of integer type, right. So, dvar stands for decision variable, the type is integer, the name of the variable is Pseudocode, right, and d comma d ensures that we have 81 variables, right. So, just like we discussed for input of d comma d, Pseudocode of d comma d will ensure that we have 81 variables and the variable can take values from 1 to 9, right. So, with this one line we have defined 81 variables which can take values from 1 to 9. Remember, we are starting the values of 0 to 8 for range, because that is what we are going to use for indicating the location. So, location we are going to start with 0 0, and then for the values that these boxes can take is from 1 to 9. Right. Now, we define the constraints. So, now we need to specify the 3 types of constraints, and also we need to specify the values which are already filled in, right. So, let us take this first constraint for all I in D, all different, all j in D, pseudocode of I comma j, right. So, this is the constraint. This constraint is to be written for I which varies from 0 to 8, right. So, the first constraint is all different within brackets all j in D pseudocode of I comma j, right. So, first let us take the value of I as 0, right. So, 0 comma j, right. So, this is the first constraint. Similarly, we will have 8 other constraints 2, 3, 4, wherein this will be 1 comma j, 2 comma j, 3 comma j, and so on, right, all the way up to 8 comma j. Now, let us look into what each of this constraint represents, right. So, over here we say all different. So, it is all different, right. So, this D has to be an uppercase D, that is what is the inbuilt function is, right. All j in D, right. So, j varies from 0 to 8. When we write j in D, D is 0 to 8. So, j takes the value of 0, 1, 2, 3, 4, 5, 6, 7, 8. So, basically what we are saying is all different of pseudocode, right, 0 comma 0, 0 comma 1, 0 comma 2, all the way up to 0 comma 8. Why 0 comma 8? Because this is fixed to be 0 and j varies from 0 to 8. So, now this constraint basically tells that the first row and all the columns should have different values. So, we are specifying that this row has to have different values, right. Similarly, the second constraint will take care of this particular row, and the third constraint will take care of this particular row. This goes on for all the 9 rows, right. So, this is what is done by this particular constraint, right. Now, let us look into the second constraint, right. So, the second constraint is similar to the first constraint, except that now we are writing for every column. So, 0th column and I we are varying in D, which is 0 to 8. Let us say we are writing the constraint for j is equal to 5. Remember, this is written for all 0 to 8. As of now, just explaining for j is equal to 5, right. So, in that case what we are doing is all different, all I in D. So, I is going to vary from 0 to 8, right. So, pseudocode of 0 comma 5, right, because j is 5, I is varying from 0 to 8, right. So, 0 comma 5, pseudocode of 1 comma 5, 2 comma 5, 3 comma 5, and so on all the way up to 8 comma 5, right. So, what this indicates is that the fifth column, right. So, 0th column, first column, second column, third column, fourth column, and the fifth column. So, all these elements over here should be unique, right. So, this all different enforces that condition that whatever elements are there in this bracket, right, that they should be different. So, now we have taken care of 2 of the constraint, that all rows should have unique values and all columns should have unique values, right. So, now let us look into the third constraint. So, to write for that 9 boxes, right, we have these 2 variables block underscore row and block underscore column, which runs from 0 to 2, right. So, this will basically write 9 constraints. So, for example, if we denote block underscore row by let us say br, right. So, br will take a value of 0, br will take a value of 1 and br will take a value of 2, right. And if we denote for block underscore column, that will also take a value of 0, 1 and 2. So, block underscore column is 0, 1, 2, again br is equal to 1, block column is 0, 1, 2, again over here 0, 1, 2. So, this line which we have below it will be uniquely written for 9 different times, right. For the first time br is equal to 0, bc is equal to 0, for the second time br is equal to 0, bc equal to 1, third time BR is equal to 0, BC equal to 2 and so on, right. So, now that we have understood this, let us see what this is doing. So, here we know that all different will enforce the condition that whatever values are represented over here are unique. So, now we define another two variable L comma M, right. So, again L comma M will take values from 0 to 2. So, let us say L will be 0, M will be 0, L is equal to 0, M is equal to 1, L is equal to 0, M is equal to 2. Similarly, L will take 1 and L will take 2. This will be M is equal to 0, M is equal to 1, M is equal to 2, M is equal to 0, M is equal to 1 and M is equal to 2. So, these 9 combinations are valid for each of the 9 constraint, right. So, because for every time we will be running L and M from 0 to 2. Now, let us see what this part of the code does, right. So, instead of Sudoku, let me just call it the variable name as x, right. So, x is equal to, so this is basically x into 3 times BR plus L comma 3 into BC plus M, right. So, for the first time BR is equal to 0, BC is equal to 0, right. So, BR is equal to 0, BC is equal to 0, this will transform to x is equal to L comma M, right, and we are saying all the variables, right. So, x, L comma M and L and M vary for this 9 different combinations. So, basically what we are saying is x 0 0, x 0 1, x 0 2, right, and then x 1 0, right, because of this combination x 1 1, x 1 2, x again over here 2 comma 0, x 2 comma 1 and x 2 comma 2, right. So, this elements if you try to locate, it is this box x 0 0, x 0 1, x 0 2, x 1 0, x 1 1, x 1 2, x 2 0, x 2 1 and x 2 2. So, this 9 elements we have been able to extract using BR is equal to 0, BC is equal to 0 and the combination of L and M varying from 0 to 2. So, we have taken care of this box, right. So, here BR is equal to 0, BC is equal to 0. For this box, if we do BR is equal to 0 and BC is equal to 1, we will get all the 9 elements over here in this box. If we take BR is equal to 0, BC is equal to 2, we will get this block. So, the same discussion holds for all the other blocks, right. So, let us just try it for BR is equal to 1 and BC is equal to 2. So, we are looking at this block, right. So, this x becomes x of 3 plus L because BR is 1 comma 3 into BC. So, that is 6 plus M, 3 into this is BC. So, BC is 2, 6 plus M, right. So, here it will be x of and L and M vary again from 0 to 2. So, this will be 3 comma 6, right. So, 3 comma 7, right. So, M will take a value of 1, then if M takes a value of 2, it is 8, right. Then L will take a value of 1, so this becomes 4, 4 6, L takes a value of 1, so 4, M takes a value of 1, right. So, 4 comma 7, right. Over here again 4 comma 8 because now M takes a value of 2, then this will be L takes a value of 2, we are just enumerating for this 9 combinations. So, 5 comma 6, 5 comma 7, M taking a value of 1 and M taking a value of 2 will give 5 comma 8. These elements are over here 3 comma 6, 3 comma 7, 3 comma 8 and then 4 comma 6, 4 comma 7, 4 comma 8, 5 comma 6, 5 comma 7 and 5 comma 8, right. So, this third constraint over here takes care that each of this block has unique values. So, this last constraint will help us to enforce the constraint that whatever boxes are already filled, the values are taken from this input of I comma j, right. So, over here we have for all I comma j in D such that, right. So, over here since I and j run over D, right. So, I is going to take a value from 0 to 8 and j is going to take values from 0 to 8, right. So, basically we are expecting again 81 constraints, right, but we are writing this constraint only in the case if input of I comma j. Input of I comma j means we are looking at the data, right. So, we look at all the 81 boxes and this constraint is written only for those combinations of I and j for which input of I comma j is not equal to 0, right. So, if we look at this particular pseudocode, let us say, right. So, there we said for all I comma j in 0 to d, right, such that input of I comma j is not equal to 0. So, we are writing the constraint only for those I comma j, right, and pseudocode of I comma j is equal to input of I comma j, right. So, I and j can initially take a value of 0 0, right. So, what we are saying is input of 0 comma 0, right, if it is not equal to 0, right, which is not true. So, this constraint is not written, pseudocode of I comma j is equal to input of I comma j is not written, right. But if we write input of, so this I and j run over all the boxes, right. So, when we write it for the second time, so first row, 0th row and the first column, right. So, this is 0th column, first column, second column, third, fourth, fifth, sixth, 7, 8 and first row, second row, third row, fourth row, fifth row, sixth row, seventh and 8th row, right. So, now if we see input of 0 comma 1, that means this particular cell, right. So, that is not equal to 0. So, this is not equal to 0. So, this condition is being satisfied. So, in this case this pseudocode of 0 comma 1 is equal to input of 0 comma 1. So, input of 0 comma 1 is 7, right. So, this constraint is enforced. So, whatever values are known, they are given as a constraint, right. Over here we have defined all the 81 variables, right. But if the pseudocode has, let us say, some 15 values filled in, right. So, we will have 15 additional constraints which will uniquely fix 15 of those 81 variables. So, here if we see, we have been able to model the pseudocode problem very easily, right. We did not even transform the problem into constraints involving less than equal to or equal to constraints, right. In IBM ILOG CPLEX for constraint programming, we have this function all different, which will ensure that all those values which are given to the function all different will be uniquely fixed. So, this is a benefit of constraint programming. The model can be given in a form which is very expressive and is similar to our natural language. So, the constraint programming technique will branch on the variables, right, and do a domain reduction to get the solution. So, let us add a new OPL project, right. This is the model which we had discussed, right. So, here we have added this line using CP so that we can solve it using constraint programming. So, this code is what we discussed a little while earlier, right, and then we are defining this range. The name of the range is D and it will have values from 0 to 8. So, basically that is 9 values, and then to specify whatever values are already filled in the pseudocode table, we use this parameter input, right, its dimension is D comma D. So, D is basically 0 to 8, so 9 values. So, input of D comma D is input of 9 cross 9. So, basically 81 elements are expected over here, and then we define a decision variable whose name is pseudocode and it is of integer data type. It will also have 81 values, right. So, pseudocode of 0 comma 0 is a decision variable, pseudocode of 0 comma 1, pseudocode of 0 comma 2 all the way up to pseudocode of 9 comma 9. So, the values that this variable pseudocode can take is only from 1 to 9, right. Remember, the range is from 0 to 8, whereas the values are from 1 to 9, because pseudocode requires that the values in the pseudocode should be from the 9 values starting from 1 up to 9. So, over here we will specify the input. So, the meaning of this is that the first row, the fourth element is 9. So, that is already filled, right. Similarly, the second row, the fourth element, fifth element, eighth element and ninth element are already filled with 8, 7, 3 and 5. So, now we have the model over here in pseudocode demo.mod and we have the data in pseudocode demo.dat and we have this configuration 1 which by default includes this pseudocode demo.mod, pseudocode demo.dat, right. So, now if we execute this default configuration, we will get the solution of the Pseudocode problem, right. This is our decision variable Pseudocode. So, if we double click on this, we have the Pseudocode table over here. So, if we remember, the fourth column was already filled with 9. So, over here if we see 1, 2, 3, 4th. So, the fourth element was already 9, right. So, this is basically the third column. This is 0th column, first column, second column and the third column, right. So, now if we look at the solution of Pseudocode, that value is as we had specified. So, similarly you can check for the rest of the elements, right. All the rows would have unique values, all the columns would have unique values and all the 3 cross 3 blocks would have unique values. So, for example, if we see 0, 1, 2 on the row and 0, 1, 2 on the column, we have 1 over here, 2, 3, 4, 5, 6, 7 over here, 8 over here and 9 over here, right. Similarly, all the constraints would be satisfied. So, this is how we can use constraint programming to easily model Pseudocode problem and solve it, right. So, here if you see, we did not transform the problem into inequalities of the type less than equal to, or we did not have constraints of the type equal to, still we were able to model the problem and solve with constraint programming, right. So, now let us see what happens if we do not have this line, right. So, using CP I have commented in IBM ILOG CPLEX optimization studio, using double slash as shown over here is to comment a particular line, right. So, here if we see, it specifies this errors, right. So, we have 3 errors, because when we do not specify using CP, it means we will be solving this problem with CPLEX and these functions all different is not supported in CPLEX, it is supported only in constraint programming. Similarly, in this map coloring problem, let us see what happens if we do not have this using CP over here. So, let us comment that, and if we now execute. So, even without using CP, right, if we solve this problem, CPLEX is capable of solving this problem despite the fact that we are using this not equal to constraint, right, which is not in the conventional form. So, when we say conventional form, remember that we wanted the constraints to be in the less than equal to form or greater than equal to or in the equal to form, right. So, though this is not in any of those 3 formats, CPLEX is still able to solve because these constraints are internally converted into the less than equal to form or greater than equal to form or as equality constraints, right. Now, we will look into the final example for constraint programming. This is a scheduling problem which requires a building of the house, similar to the other 2 problems, map coloring as well as Pseudocode problem. This is also a constraint satisfaction problem, as in it does not have an objective function, but it has a set of constraints which need to be satisfied. In this example, we have these 10 tasks which are to be satisfied while constructing a house, right. So, masonry, carpentry, plumbing, ceiling, roofing, painting, windows, facade, garden and moving into the house. So, this specifies the duration of each task. So, these are the tasks which need to be completed, and let us say masonry requires 35 days, carpentry requires 15, plumbing 40, ceiling 15, roofing 5 and similarly the other values, right. And then we have these constraints, right, that carpentry can be started only after masonry is completed, right. Similarly, plumbing and ceiling can be started only after masonry has been completed. Roofing can be started only after carpentry is completed, right. Carpentry in turn can be started only after masonry is completed. So, facade can be started only after roofing and plumbing. Roofing in turn requires carpentry to be completed and carpentry in turn requires masonry work to be completed. So, the decision variable here is to determine the start time of each task. So, the decision over here is when to start a particular task such that these constraints are obeyed, right. So, over here we will be using CP. So, that is why we have using CP, and in IBM ILOG CPLEX optimization studio we have a decision variable, right. So, this dvar is decision variable of the type interval, right. So far we have seen dvar to be int or float positive, right. So, there are various other types of decision variables also. For constraint programming, one such decision variable in terms of scheduling problem is interval. So, this interval is also a keyword. These are the names of the decision variables, so which is nothing but our tasks, and for decision variables of the type interval we can also specify something called as size, right, and the size over here is the amount of time required to complete that particular task, right. So, here we are defining the data as well as we are defining the decision variables. Remember, in this statement dvar, interval, size, all these 3 are keywords, right. The name of the variable is moving and the size is the time that it requires. So, similar to the all different constraint we had for solving the Pseudocode problem, right, we have something called as end before start. You can call it as function or construct, right. So, end before start requires two values, right. The first value should be the task which has to be completed before the second value is started, right. So, in this case we want the carpentry to be completed before we begin masonry work, right. Similarly, we want the masonry work to be completed before we start the plumbing, right. So, end roofing before starting garden, right. So, over here end garden before start moving, right. So, since this inbuilt construct is already defined, it is very easy to specify these constraints. So, these are basically the requirements which we have shown in this table. So, when we solve, this is the solution that we would be getting. So, it indicates masonry is to be started at 0, it has a size of 35 and it will complete at 35, right. So, if we have a Gantt chart over here wherein this is time. So, the masonry work is to start at 0 and it will go on for 35. So, this will be 35, right. So, this is let us say masonry. So, after that carpentry starts at 35, completes at 50, right. So, let us say this is carpentry. So, this is 50. The duration of carpentry, if you remember, it is 15. So, plumbing starts at 35 and continues till 75. So, over here 35 plumbing starts and let us say this is till 75. So, this is plumbing, and similarly at the same time we have ceiling, right, which starts at 35 and also gets completed along with carpentry, because both of them start at the same time, their duration is also the same, hence their ending time would also be the same. So, for at 35 we also have ceiling which is getting completed, right, by 50. So, at 50 we have these two tasks which are started, right, roofing and painting. So, painting will complete at 60 because it has a duration of 10, whereas roofing will get completed at 55 because it has a duration of only 5, right. Similarly, you can analyze the other decision variables, right. This example is already available. So, we just need to import it, file import example and double click on this, right. So, in basic we have scheduling. So, we have this SCHED underscore intro, right. So, this is the house building introductory problem for constraint programming. So, if we click over here, right. So, we have the model over here. So, we will not look into this particular section. So, we will comment this particular part, right. So, we have commented it, but if you are interested you can look into the help of IBM ILOG CPLEX optimization studio to understand what is happening over here, right. Since this part of the session is just to let you know the availability of constraint programming in IBM ILOG CPLEX optimization studio, we are not looking into this, right. We will just restrict it to preliminary details. So, over here it is the same thing which we have discussed previously, right. So, the decision variables are defined. The type of the decision variable is interval, the name of the decision variable are the tasks which we are performing. So, when we have this interval decision variable, we can also specify size. So, additional details on this interval variable you can look into the help of IBM ILOG CPLEX optimization studio, right. So, here whatever size is given to us we have specified that type. So, this type of decision variable is available only with constraint programming, right. So, we have this using CP, and this construct is also available only with constraint programming. So, end before start is one such example. There are various other constructs which are available in this software, right. So, we specify whatever were our requirements, right. So, now if we execute this, so we get the solution. So, masonry is to be started at 0, it is going to continue for 35 time units and it will get completed at 35 time units. Similarly, carpentry will start at 35 time units, it will get completed at 50 as it has a duration of 15. So, here you can look into the statistics, right. So, here it has 14 constraints, 10 variables. So, in this session we have introduced you to constraint programming feature which is available in IBM ILOG CPLEX optimization studio. Here the intention was not to teach you constraint programming, but just to let you know that there is something called as constraint programming which can help in easier modeling of the problem in certain instances. So, with that we will be concluding this session. In this session we saw 3 constraint programming examples. One was map coloring problem, the house building problem which involved scheduling, as well as the Pseudocode problem. That brings us to the end of this course. In this course, we looked into regression, we looked into 5 meta-heuristic optimization techniques, teaching learning based optimization, particle swarm optimization, differential evolution, genetic algorithm, as well as artificial bee colony optimization. We also looked into how to handle constraints, both using a penalty approach as well as using a correction approach. We also looked into the production planning problem, wherein we demonstrated the performance of some of the techniques which we discussed, both using penalty approach as well as using the correction approach. We then looked into 3 state of the art optimization software: MATLAB, IBM ILOG CPLEX Optimization Studio, as well as GAMS. We also briefly touched upon how to solve linear programming problems as well as how to solve mixed integer linear programming problem using CPLEX as well as the branch and bound technique. We hope that you would have found this course to be useful. Again, remember that this is just an introductory course into optimization, right? You can also look into various other optimization techniques which are regularly proposed. In this course, we did not dwell too much into mathematical programming. You can look into other courses which dwell in detail in mathematical programming. We hope that you will be able to use optimization in your everyday activities. This course would have not been possible without the help of the 2 TAs, Debashish Maharana and Ramya Komodar. With that, we will conclude this session. Thank you.